Well, I think we can start our afternoon session. And our first speaker is Professor Chris Hall from Imperial College London. And Professor Chris Hall is a long-term expert in supergravity, superstring theory, and M theory. In particular, he has been focusing on the string dualities and duality invariant formulation of string theory, including generalized geometries and double fields. But today, he's going to talk about degeneration, geometry, and duality. Please go ahead.
Okay, thank you very much. Right, so I'm going to be talking about some slightly older work pre-COVID with my student, my then student, Nipol Chamjamras, and also some more recent work following up on that, which is yet to appear. So the story of dualities in string theory is now quite a very interesting one. They've revealed the non-perturbative structure of string theory, that it's the theory of branes as well as strings. And a key part of this is, one of the, a central part is played by T-duality, which if you've got a space-time which has got a toroidal fibration, it gives a duality transformation which applies so long as the torus action on the space acts isometrically. And what I want to talk today is about generalizations of this without isometries. So one early place where a hint of this was seen is in the SYZ construction, which relates mirror symmetry to T-duality in the Kaluza-Yau. But properly speaking, Kaluza-Yau manifold has no isometries, and so although it does have approximate isometries in a large volume limit. And so there's a question about really what this T-duality is that plays a role related to mirror symmetry. And one of the things we'll see is that thinking about these kinds of ideas gives a new way to think about special holonomy geometry, Kaluza-Yau and its generalizations, and relating it to brane constructions. And so I think it makes quite an interesting story. So my starting point is a duality from my work with Paul Townsend, my paper on dualities from 30 years ago this year, where one of the dualities we talked about was the duality between 2A strings compactified on K3 and heterotic compactified on T4. And we now know that the heterotic string is dual to type 1, and so we can think about this also as a duality with type 1 on T4. Now, this could be understood at a special point in moduli space by a chain of T-dualities and S-dualities. So starting off with type 1 compactified on a 4 torus, then applying a series of S and T-dualities, one arrives at 2A compactified on a 4 torus modded out by a Z2, which is an orbifold limit of K theory, of K3. In other words, it's the K3 surface, the 4-dimensional compact hyperkähler space at a special point in its moduli space. And then the idea I want to develop is to look at moving to other points in the moduli space where there are no isometries and so no T-dualities. In the K3 moduli space, we know that moving away from this special point in the moduli space will give a more general K3 metric, one which isn't an orbifold and which no longer has the T-duality as isometries. And moving to other points in the moduli space of type 1 on T4, we understand in terms of moving positions of branes. And so by matching the two deformations in the two moduli spaces, should give us a way of understanding the duality between these two theories at general points in the moduli space. So in looking at this chain of dualities relating these two, we see that the D-branes which play a role in type 1 are dual to Kaluza-Klein monopoles. This duality between the branes which play an important part in understanding the type 1 theory on T4 and the Kaluza-Klein monopoles, which we'll see play an important role in understanding how the geometry on K3 works, and understanding the relationship between these two will be a central part of my talk. But in the type 1 theory, there are also orientifold planes which play an important role. And one of the questions I want to explore is what happens to these under these dualities. Do these have some sort of geometric dual? And what does these mean in the context of the geometry of K3? And as a result, it will give a new picture of K3 and a new understanding of the role of the orientifold planes and understanding the strong coupling limit, and in particular will give an explicit picture of some of these dualities. So if we, just to explain a little bit more about what we're going to do, if we consider type 1 theory, type 1 string theory, which is a theory of closed and open strings in superstrings in 10 dimensions with an SO32 gauge group. If one compactifies on a circle, so we're on 9-dimensional Minkowski space across a circle, and then we T-dualize on that circle, then we end up with a theory on 9-dimensional Minkowski space across S1 over Z2. So the T-duality forces us to take an orbifold of the S1, and this is, if we take S1, this corresponds to the Z2 corresponds to a reflection, so it folds two halves of the circle over to give a line interval. So this gives a theory on a product of 9-dimensional Minkowski space across a finite line interval. And in this picture, there are 16 D8 branes moving along the interval, and there are O8 planes or orientifold planes at the ends of this interval, which and these branes all fill the 9-dimensional Minkowski space, but they're localized on the S1 mod Z2. That's the conventional picture in the perturbative string, but at strong coupling, there's some extra things which happen. There's new kinds of orientifold planes which can arise, which have so far been quite mysterious. And so one of the aims is to understand these a bit better. And what we'll see is this picture is dual to a degenerate limit of K3 with a long neck region and with Kaluza-Klein monopoles moving along the neck of this K3. And in such a way that the positions of these Kaluza-Klein monopoles correspond to the positions of these D8 branes. And so there's a matching between the moduli spaces in these two cases. And this degenerate limit was of K3, which in some sense could be thought of as being predicted by the chain of dualities. In fact, is also, it turned out, had been constructed by mathematicians shortly before our work. And so what we find is a validation of our arguments very explicitly in terms of an explicit geometry. And the ends of this long neck are capped by geometries which are dual to the orientifold planes in the type 1 theory. And these are very interesting geometric spaces which become known as Tian-Yau spaces. And understanding these, the geometry of these helps understand this mysterious strong coupling behavior at weak coupling and geometrically. And there's some interesting relations with the geometry of Del Pezzo surfaces, which comes up in this story. So I mentioned mirror symmetry, and in particular, there's the SYZ picture of mirror symmetry, where if you have a Calabi-Yau n-fold, it has a fibration, at least locally, over a base, with special Lagrangian fibers which are n tori. So this is n complex dimensions. So as a Kaluza-Yau threefold has a 3 torus fibration. Although not quite. I mean, it turns out the fibers degenerate at a set of points, and so it's really a fibration over the complement of the set of points where it degenerates. And the mirror Kaluza-Yau has a dual, a similar fibration, but with the dual tori over the base. And so the mirror symmetry could be understood as they argue to be understood as a T-duality of these torus fibers. So in the large volume limit, the torus action becomes approximately isometric, and in the infinite volume limit, it becomes a real T-duality. But at finite volume, it's not a real T-duality, and yet we still believe that there's a mirror symmetry, in particular that the string compactification on 2 mirror manifolds gives identical physics. And so this is not, so if the mirror symmetry is not related to T-duality, it's not precisely T-duality, but something to do with it, this suggests that there should be a notion of some generalized T-duality which works in this case. And we'll see this very explicitly for the K3 metric which emerges from our discussion. So let me now start going into this story in a bit more detail. So first of all, I want to consider an example of a chain of configurations related by T-duality. And these will all be of the form of a 2 torus fibered over a circle. But in fact, I'll really be talking about the conformal field theory on a 2 torus, on which there's a T-duality group O22Z which acts. And so I'll be looking at bundles where we allow monodromies which not just in diffeomorphisms, but in fact in O22Z, the T-duality group. So an important part of this group is given by a product of SL2Zs, one acting on the complex structure modulus of the 2 torus and one acting on the Kähler modulus, which is the constant B field plus I times the area. So we'll start off with a simple case of a 3 torus. So we have geometrically we have a trivial bundle, but we have a non-trivial H flux, B field flux over this 3 torus. So we can choose B to be given by some integer from the normal. It's an integer because we require the flux to define an integral cohomology class. And so B could be written, for example, in this way. And so if x is the coordinate on the base, as x goes to x plus 2 pi, we see that B shifts by m times 2 pi, but I'm suppressing some factors of 2 pi in these formulae. And so that corresponds to a monodromy as this 2 torus goes round of rho going to rho plus m, even though the metric is flat. So this is an example here. Then if we do a T-duality on one of the circles here, then it turns off the flux, but gives rise to a non-trivial 3 geometry where we have a 2 torus fibered over the base, where as one goes around the base, the 2 torus comes back to itself by a large diffeomorphism of the 2 torus, which corresponds to a monodromy in which the complex structure modulus shifts by m. This could be thought of as giving a 2 torus bundle over a circle, or equivalently, or also as a circle bundle over a 2 torus, where m is the first Chern number. And this is a famous space of 3-dimensional manifold known as the nil fold, or sometimes the nil manifold. A further T-duality then gives a monodromy, which is a non-trivial transformation of this kind, which means that it's not a geometric transformation, and this gives something which has got a T-duality transition function, or in other words, something which is proposed the name T-fold for. So it's it has a T-duality monodromy, and it looks as if the metric and the B field are badly non-periodic, because remember, x is a periodic variable, and so shifting x to x plus 2 pi is clearly gives a metric which isn't periodic and the B field which is not periodic. But what happens is that the metric and the B field come back to themselves related by a T-duality transformation, which is precisely this SL2Z transformation. So this gives a nice set of examples, but it turns out that none of these is a solution of string theory in its own right. But interestingly, you can find solutions of string theory in which these appear as fibers of some vibration. And then the T-duality can be thought of as acting fiber-wise. The duality can be thought of as acting fiber-wise. And the simplest case is where we fiber over a line. So we have a space which is locally aligned times these three-dimensional configurations we've been talking about. And the simplest case is the nilfold fibered over a line, which it turns out defines a hyperkähler manifold, and hence a conformal field theory. So to see that, I remind you about the Gibbons-Hawking metric, which is a four-dimensional metric with defining a hyperkähler geometry or a self-dual geometry, so it's gravitational instanton. So it has a space where we have three coordinates, which I'll, for perverse reasons, I'll call tau, x, and z, and a fiber coordinate y. And so we have R3, or rather R3 with a set of points removed, and then we have a circle bundle over that. And this omega is a one form with satisfying this equation, and V is taken to be to have delta function sources. So V has given. So we'll assume that that there are delta function sources to the stress tensor, so that the V is of the form of this form, where A is A can be taken to be 1 here, and M are integers, and the Ri's are some set positions in R3, and this is interpreted as giving rise to, this gives rise to a multi-Taub nut or Gibbons-Hawking metric in Euclidean signature. What else will I say? And yeah, and it turns out that at least when there's one source, that these points can be, in fact, the source is regular, and more generally, there are orbifold singularities of these points. Now, if we take this space and its product with R15, it defines completes an exact solution of the string theory, because this is a hyperkähler manifold. The corresponding sigma model is precisely conformally invariant. And this space is interpreted as giving a Kaluza-Klein monopole space, multi-Kaluza-Klein monopole space. So here, this three-dimensional space is interpreted as the transverse space, and the Ri are taken as the positions of the Kaluza-Klein monopoles in this transverse space, and the remaining dimensions define the world volume of the Kaluza-Klein monopole. So I'll be interested in the case where we take this, so going back. So V is a harmonic function on R3, and this, which I've taken to be of this form in the usual case. But in fact, we could take V to be independent of one or more of these coordinates, and then we'd be looking at a harmonic function instead of on R3, on R2 or R1. So I'm going to be looking at V, which is independent of two coordinates, X and Z. And so something said as we think of it as smearing over X and Z. And so it depends, we've got a harmonic function of one variable, which means it's a linear function. And because everything's independent of the X and the Z, we can take X and Z to be periodic. The resulting metric is typically singular, and we'll say more about it in a moment. So locally, the general solution will be V tau is M tau plus C. But in fact, we can also look at piecewise linear solutions where we have some jump in the gradient. And at this kink here, we'd say that there's a domain wall, which dividing the space into two parts. And the jump in the gradient is the energy or the energy density or tension of this corresponding domain wall. So here, if we look at the given Hawking metric with smeared over two directions, so V just depends on tau, and it's taken as periodic in X and Z, then for fixed tau, we get precisely the nilfold metric we talked about before. So we see that this geometry is giving something which is fibered over a line, the line with coordinate tau, and there's fibers which are the nilfolds as advertised. And there are domain walls which split the space into different regions, for different regions of the tau, the line in tau, and jumping over the domain wall corresponds to gives a jump in the degree m of that. And for the string solution, we have a product with R15, and so these are smeared Kaluza-Klein monopoles. And here the domain walls are 8 branes in 10 dimensions, splitting, so they have a 9 plus 1 dimensional world, 8 plus 1 dimensional world volume transverse to the tau line. So we've seen that T-duality takes relates the nilfold to a T3 with flux. And so if we fiber over a line, the T-duality we would expect to take as the T3 fibered over a line. And that's indeed the case. And the resulting geometry from the T-dualizing the given Hawking metric gives something which is conformally flat. And it gives a three-form flux, which is given which is proportional to the gradient of the tension. And again, we can have this as being piecewise linear, and there's also a dilaton where this is. Sorry. Yes, that's right. Yes. So it's the T-duality we talked about. No, sorry, it's in one direction. T-duality in one direction relates the two. So we started off by looking at the 3 torus with H flux, and then T-duality on any one direction, it doesn't matter which one, will give a nilfold, which will turn off the B field, and it's that T-duality I'm using here. And I talked about a chain of dualities. If I did more dualities, then it would take this to the T-fold, and there'd be a corresponding story there. So for the purpose of this talk, I'm going to concentrate on just the nilfold and the 3 torus. But there's a chain of T-dualities which would go along with this, and so there's always an interesting story about what happens if one does more T-dualities. So this fits together into a 10-dimensional solution for taking the product with 6-dimensional Minkowski space. And this solution has the interpretation, this is a Nerva-Schwarz 5-brane solution, but where the Nerva-Schwarz 5-brane which has a transverse space in the tau, x, y, and z coordinates, as you can see from here, but we're taking it to be smeared over the x, y, and z. So the harmonic function, instead of being a harmonic function in R4, it's just a harmonic function on the line. And because of that, we can identify the x, y, and z coordinates to give a transverse, so that we're talking about a Neveu-Schwarz 5 brane with a transverse space R cross T3 instead of T4, instead of R4. So we can glue these together in the obvious way to get multi-domain wall solutions by having a piecewise linear function for V. And one can also talk about a single-sided domain wall. So if one takes V to be of this form, then this is invariant under the reflection tau to minus tau. So if we quotient by this, this will give a solution with just the, say, positive tau. And this has been suggested could be interpreted as a single-sided domain wall at tau equals 0. So for both the Kaluza-Klein monopole picture and the Neveu-Schwarz 5 brane picture, we can smear on T3 and get the geometry and look at the multi-solutions we were talking about. But from the Neveu-Schwarz 5 brane smeared on T3, we can first of all do a S-duality, taking it to a D5 brane. And then if one does a T-duality on all three directions of this 3 torus, which we can do because it's periodic in T3, it changes the D5 brane to a D8 brane, which is wrapped on this T3. And so it takes the multi-NS5 brane solution to a multi-D8 brane solution of that kind. So this gives a nice map between these solutions, but there's still a problem, which is that these spaces are singular. They're singular at the points where you have the domain walls, and there's this jump in the gradient. And they're also singular, and also because the dilaton was linear with the direction, increased with tau, if tau went on indefinitely, it would blow up. And so the way of avoiding that is to end the tau direction with some single-sided domain walls. So in other words, one has a line interval with single-sided domain walls at the end. But then to solve the equations, one needs negative brane charges to give net zero charge. And there's a problem about how to set all this up. So if we go back to this configuration with D8 branes wrapped on T3 arranged along a line, then there's a string theory setting which gives a consistent configuration of this, which is the type 1 prime string theory, which gives a consistent setting for D8 branes arranged along a line interval. Provided there are precisely 16 D8 branes, and at the ends there are O8 planes, orientifold 8 planes at the ends. So let me say a few words reminding you about what the type 1 prime string theory is. So first of all, the type 1 string theory is a theory of open and closed superstrings in R91 with gauge group SO32 carried by Chan-Payton factors at the ends of the open strings. And this can be understood as arising from a Z2 quotient of the type 2B string theory by an operation omega, which serves as to invert the orientation of the world sheet. So it's orientation reversal on the string world sheet. And the type 1 theory can be thought of as having one space-filling O9 plane corresponding resulting from this orientifold. The orientifold means is just the word given for quotienting by a parity reversal on the world sheet. And this is, turns out to have a charge in certain units of minus 16. And this is cancelled by saying that there are 16 D9 branes, each of charge 1, which carry the Chan-Payton factors. And of course, in 10 dimensions, because the 9 branes are space-filling, these are all on top of each other, and there's not much room for anything to happen. But one reason for thinking of things this way is seeing what happens to this as we do T-dualities. So now, if we compactify the type 1 on a circle to get 9-dimensional Minkowski space across a circle, then if we T-dualize on this circle, we start off with a Z2 quotient of the 2B theory. T-duality on a circle takes 2B on a circle to 2A on the dual circle. So we'd expect to get a Z2 quotient of the 2A theory. The naive expectation would be that you just get the modifying by the orientation reversal on the world sheet of the 2A theory, but that turns out not to be right. A more careful analysis shows that you need to, that the T-duality maps omega to omega map composed with a reflection on the 9-dimensional coordinate, the circular coordinate, so that this takes, so S1 over R9 is the Z2 orbifold of the circle, which gives a line interval, as we discussed earlier. And there's an O8 plane, an orientifold plane at each end of this line interval, each of which is associated with a charge minus 8. So we went from an O16 plane with charge 16 to 2 of charge minus 8, and 16 D8 branes of charge 1, which again cancel the charge. But now the D8 branes can be move anywhere along the line interval. So for the D8 brane, the string background needs orientifold planes, and there are singularities at the domain walls, but in this in the corresponding supergravity solution, which we'll look at in a moment. But these singularities reflect the presence of physical objects, the D8 branes. And in the dual type 1 prime theory, we get 16 D8 branes and 2 O8 planes. And now we can look at doing further T and S dualities to relate this to the Nerva-Schwarz-5 brane configuration and to the K3 configuration we were talking about earlier. So in particular, there'll be the question arising as to what the duals of the O8 planes will be, both for the Nerva-Schwarz-5 branes and more interestingly for the K3 geometry. So if we look at the supergravity solution corresponding to the type 1 prime theory, we have a line interval across 9-dimensional Minkowski space. We have 16 D8 branes, each of charge 1, and we'll arrange them at points tau I along the line interval. And we have orientifold plane of charge minus 8 at the endpoints, which are taken as tau equals 0 and pi, and we have this solution. And the charge conservation means that the sum of the charges, which in each case is the jump in the gradient, the charge at each brane is a jump in the gradient, and the total charge is 16. Or we could move some of the D8 branes to one end, and so the charge at the end will be minus 8 plus n minus, and n plus of them move to the other end, and so we get charges b minus and b plus. And so the sum of the D8 brane the remaining D8 brane charges would be this number, which would be less than or equal to 16. So now we look at the dualization of this story. If we dualize the supergravity solution wrapped on T3 to get a smeared Gibbons-Hawking metric and another Schwarz five-brane solution with the same potential V on the interval. Under these dualities, the D8 branes become Kaluza-Klein monopoles or another Schwarz five-brane smeared over the T3 in the way we've seen. And then there's a question about the singularities which arise from these smeared branes and how are they resolved. And in particular, at the ends of the intervals, there are the duals of the question about what the duals of the O8 planes will be. So the chain of dualities, which take the D8 brane to the D5 brane to the another Schwarz 5 brane, and then the Kaluza-Klein monopole, then a further T-duality would take it to something which is sometimes referred to as an exotic brane, which is a T-fold, and I won't be saying a lot about those. I won't be saying much about those today. And then the corresponding transformations of the orientifold planes takes these to something which has been called an ON plane, has been discussed in the literature as the orientifold corresponding to the kind of plane corresponding to nervous Schwarz five-brane geometries. But there's a question about what the geometric dual of these will be corresponding to the Kaluza-Klein monopoles. So these orientifold planes can be thought of as being negatively charged branes along here. And so the question is, what are the negative charges corresponding to the Kaluza-Klein monopoles which might arise here? So we can look at this in the full string theory and with the full dualities, and then things are much more, and then things are quite clear as to what's going on. So the type 1 prime string theory is dual to the type 1, and so this remains true when we compactify on a 3 torus. Type 1 primed on a 3 torus is type 1 on a 4 torus. And so we can look at the chain of dualities we talked about earlier, which take us from the type 1 theory, which is 2b modded out by a Z2 quotient of the 2b theory. Then under each of these changes, the dualities take the 2b to a 2a or a 2b theory. And in each case, we end up with a Z2 quotient of each of those theories. And it turns out that these are what one gets here. So R6, 7, 8, 9 means a reflection on each of the 4 directions of the 4 torus, which are the directions 6, 7, 8, and 9. And the last step gives a 2a with just a geometric quotient. So it's just a geometric quotient of the T4, which is the orbifold limit of K3. So this is the duality between the heterotic or type 1 on 4 torus and K3 at a special point in its moduli space from the chain of dualities that we talked about earlier. So these are the slides from the 2 lines from the previous slide. And so there's a question about what happens to the orientifold planes. So in each case, for the normal orientifold planes, each T-duality doubles the number and halves the charge. So on a 4 torus, we go from one plane to 16 planes, each located at each of the corresponding to the 16 fixed points under the Z2. And so there's a question about what the last step would be here, corresponding to the Kaluza-Klein monopole. That suggests that there should be some smooth geometric dual to orientifolds. And so there's a question about where are the orientifolds in the K3. So putting this together, we've looked at dualizing the supergravity solution with the D8 branes to one with Kaluza-Klein monopoles. The space, which is a nilfold fibered over a line with smeared Kaluza-Klein monopoles. And the ends of the line would be some geometric dual of the orientifold planes. And we've seen that dualizing the string takes you to the 2a on K3. So this predicts that if we can match the moduli spaces in the way that I suggested earlier, that it predicts there should be a region of the K3 moduli space which corresponds to the type 1 prime moduli space. So it's a subspace of the full moduli space of K3, where the K3 looks like a nilfold fibered over a line interval with 16 Kaluza-Klein monopole insertions, and where the regions of the K3 at the ends of the interval looks like the orientifold of the O8 planes. And so this is the sort of picture which is proposed by this chain of duality arguments. And remarkably, just such a degenerate limit of K3 was constructed a few years ago by mathematicians. And they constructed a family of K3 metrics with a long, they constructed precisely this kind of K3 limit that I had in mind, that I was anticipating. So if they find a family of K3 metrics which have a long neck region. Each segment of the neck corresponds to a nilfold or nil manifold fibered over the line. There are different values of the degree of the nilfold in different segments, and the jump in M is associated with an insertion of a gravitational instanton, the Kaluza-Klein monopole. And the ends are capped by some remarkable non-compact hyperkähler spaces which were constructed by Tian and Yau. And these are complete hyperkähler metrics which are have precisely the right asymptotics to join onto this geometry. They're asymptotic to a nilfold fibered over a line as we required. So here's a picture from their paper of what this geometry looks like. So here they're looking at a particular case where there's just one segment. There's these crosses denote the positions of the Kaluza-Klein monopoles. These caps at the end that represent the Tian-Yau spaces. And the lines up here correspond to the nilfold fibers, and here we have the tau direction is along this direction. So the first approximation to their K3 metric is precisely the solutions we've been looking at. So the multi-domain wall solution we've been talking about, and they resolve the domain walls using an Aguri buffer construction, which I'll explain in a moment. They resolve the single-sided domain walls with the Tian-Yau spaces, and the hard part of their paper was proving that you can glue these pieces together in a controlled way to get a smooth K3 metric. So first of all, the Aguri buffer construction. So we want a given talking metric in which the transverse space R3 is replaced by R cross T2. The first approximation which we've talked about is smearing over the T2. But what Aguri and Buffer did was take the given talking metric with a set of sources in R3 and takes a periodic array of these sources arranged in the XZ plane and find a way of taking the infinite sum, regularizing the infinite sum in a way which gives a solution which is regular on some finite interval in the transverse space R with coordinate tau. And the Tian-Yau spaces, as I mentioned, are non-compact hyperkähler spaces constructed from a del Pezzo surface, which are asymptotic to the given talking metric on a nilfold of degree B times R. And an important thing is that precisely the degrees B, which is 0 up to 9, are allowed by the geometry. So saying a little bit more about the given talking about the Aguri buffer construction. Near each of the sources, the end center we get a solution which looks like an end center multi-tau nut, or one source with charge n, an orbifold singularity. And they describe this as saying that there's a bubbling limit, or a limit where you focus on these regions near these sources, which takes you to the multi-tiled nut solution. So if you take the n-center multi-tiled nut, you get a regular solution. If you take the coincident one, you get an orbifold limit of the K3. And for n sources, there's a regular hyperkähler metric for some finite interval in this tau region. And far enough from tau equals 0, we get, it looks closer and closer to the Gibbons-Hawking metric that we talked about. And now for the, as for the Tian-Yau spaces, these are complete non-singular compact hyperkähler spaces, and they're constructed from Del Pezzo surfaces by taking out a certain region, a smooth anticanonical divisor. And these Del Pezzo surfaces are complex algebraic surfaces classified by their degree, and precisely a finite set of degrees is allowed. So these are all Kähler four manifolds with positive first Chern class. Another way of thinking about these is that the Del Pezzo of degree 9 is CP2, and the degree B Del Pezzo can be constructed by blowing up 9 minus B points in this CP2. And there's a second one of degree 8, which is CP1 cross CP1. Now, the Tian-Yau space MB of degree B is constructed from the Del Pezzo of degree B, and it turns out to have precisely the asymptotics that I advertised, giving a nilfold of the right degree. And we can extend this to degree 0 by including the space T3, so that we get a space which is asymptotic to T3 cross R. So if we put all this together, we glue together these spaces, we get Tian-Yau spaces of degrees B minus and B plus, where each of these is in the interval between 0 to 9. And then looking at the jumps in the, so each Kaluza-Klein monopole gives a jump in the degree of the nilfold Ni, and the total of these jumps, so that in other words, the total of the Kaluza-Klein monopole charges must be B minus plus B plus, which is less than or equal to 18 because of this inequality. So this is almost entirely agrees with with the formula we got in the type 1 prime picture, except we've got an 18 here instead of a 16, which we got from the brain picture. So that turns out to be rather interesting. So the story we talked about for the 16D8 brains and 208 planes is correct for the Polchinski-Witten discussion of the perturbative type 1 prime theory. But Morrison and Seiberg showed that a strong coupling, the 08 plane can emit one more D8 brain to leave a plane, an orientifold plane called the 08 star plane of charge -9. And then having these at either end, and you would allow having 18 D8 brains on the interval. And if we allowed this, then we would get precisely the same formulae as for the as it arose geometrically, again with 16 replaced by 18. So both cases have 18 sources, and both allow, for example, SU18 gauge symmetry to arise from coincident sources. If we look at matching the moduli spaces, the type 1 prime moduli space is this coset, and this includes the 16 D8 brain positions, the dilaton, which is this factor here, and the length of the line interval of the radius of the S1. And under the chain of dualities, this will give an embedding of the type 1 prime moduli space in the moduli space down here. So it will construct a subspace of the K3 moduli space corresponding to regions where the K3 has the long throat geometry we just talked about. And following this through, we find that the positions of the D8 branes translate into the moduli positions from the Kaluza-Klein monopoles. We get a long net, but the ends pinch off, and the moduli come from the positions of the branes, as I mentioned. So this gives then a duality between the heterotic on type 1 on T4 and the 2A on K3. I understood as explicitly as a chain of T and S dualities at the orbifold point when K3 is the orbifold T4 over Z2. But this is not understood, but this argument does not work at general points in the K3 moduli space where there are no isometries. However, the moduli spaces of the two theories are the same, and so duality at one point in the moduli space translates to duality at all the other points, where one can translate moving in the type 1 moduli space to moving in the type 2A moduli space, even though the route between them is not a conventional T-duality. We can think about it as, for example, first of all, moving in the moduli space back to the invariant point, then doing a change with T and S dualities, and then moving away from the moduli space the corresponding amount. So we can return to the story of the relationship between mirror symmetry and T-duality from the SYZ conjecture. Here we have an approximate version of the K3 geometry, which does have isometries in a controlled approximation. So we have this, particularly, we have this long neck region, which is approximately a nil fold across an interval. The nil fold has a T2 fibration, and one can do on these fibers, so on this geometry, you can do a T-duality in these two torus directions, and we can do precisely the duality which takes this in two directions, which preserves the complex structure modulus and inverts the Kähler modulus. So this, if we do this here, then the monodromy, the nil fold is unchanged because tau doesn't change. And the net effect in this case is one that it leaves the K3 geometry invariant. The net result is just a diffeomorphism of the geometry. And so in this case, applying the SYZ prescription gives a diffeomorphism which is preserving the geometry, which is natural in this case because there was not a natural mirror for it to transform to. So we see that this is true in the approximation, but this then implies that this should extend to the full exact geometry, that the corresponding mirror symmetry should be one leaving the K3 invariant. I mentioned, so the Del Pezzo's surfaces, which played an important role in this story, are rather interesting. They crop up in lots of apparently unrelated places. They have intriguing relations to the U-duality groups and to branes, etc. And much of the math structure of toroidal compactifications of M-theory are mirrored in the mathematics of Del Pezzo surfaces. And there's been lots of papers speculating on the meaning of this. And the role of the Tian-Yau spaces and their relation to the K3 give yet another link to the Del Pezzo surfaces. So in the little time remaining, I'll just say a few quick comments about generalizations to higher dimensions and to special holonomy spaces, there's a story in which the three-dimensional nilfold we've been talked about is replaced by some higher dimensional nil manifold. These manifolds can be thought of in in a number of ways, including it can be thought of as the quotient of a nilpotent group by a discrete subgroup, or as a torus bundle over a torus, or a torus bundle over a torus bundle over a torus, and so on. And this story is related to some special holonomy metrics on these such nil manifolds fibered over a line. So this is the analog of the Gibbons-Hawking story, where we saw that the nilfold fibered over a line gave rise to a Gibbons-Hawking metric. The higher dimensional nil manifolds fibered over a line turn out to give special holonomy metrics. And T-dualizing these then relates not to simple brane geometries, but geometries of intersecting branes. And this is what one would expect, because the special holonomy generalizations have got, in higher dimensions, have got less than half supersymmetry, and one can construct intersecting branes configurations which do just that. So in 4 dimensions, we have the case we've considered, where we have a circle bundle over a torus, giving a nil manifold with SU2 holonomy. In 6 dimensions, there are 2 cases which give SU3 holonomy, or Kaluza-Yau geometry, S1 over T4 and T2 over T3. In 7 dimensions, there are 2 G2 geometries, and in 8 dimensions, there's a SU4 holonomy and a spin 7 holonomy case. So we can look at the effect of the T-duality in this case in the way we talked about earlier. We saw that T-duality takes this space to itself. In 6 dimensions, the T-duality on the 3 torus fibers, in fact, turns out to take this case to this case. So this gives explicitly a mirror symmetry, which is acts non-trivially and takes the geometry associated with this to the geometry associated with this. So here we're talking about the 6-dimensional geometry, which is fibered over a line, and where the fibers are circle bundles over a 4 torus, for example. So to show what this looks like, so in this case, we have that it's associated with this nilpotent Lie algebra, which has got this these structure constants, and the corresponding metric, the 5-dimensional metric, is given by this, which we can then fiber over a line with a function v, which is piecewise linear. And then the remarkable thing is that this geometry turns out to have SU3 holonomy. So I've already talked about the mirror symmetry acting here. And this story has some extensions to more general nil manifolds. But let me just give a slide giving the outline of some of the things explored in these papers. So there's a T-duality which takes the Taub-Nuts geometry to the Lewis-Schwartz 5-brane geometry, which generalizes to multi-instantons and multi-5-branes, multi-Kaluza-Klein monopoles and multi-5-branes. And there's a corresponding T-duality then which takes the special holonomy metrics constructed by the authors Gibbons et al., which I mentioned earlier, which arose from special supergravity solutions. And these are the special holonomy metrics given by nilfolds fibered over a line. And then it turns out that dualizing these gives intersecting 5-brane solutions with one function. And then with my student, we generalize this to more general solutions with several functions over here, which then to translate back to giving a special holonomy solution with several functions. And in these are solutions which are highly smeared, but to some extent there can be some unsmearing of this to give what is referred to in the literature as semi-local solutions over here. So it's not a fully localized brane solution, brane intersection geometry, but one which is so-called semi-local. It's local in some of the branes and not others. And this gives to a more general class of a very explicit special holonomy metrics. So I would, I'll skip those. So a key question is then whether there are fully localized non-singular solutions. And it's very interesting to use the intersecting brane picture and the corresponding and related to brane webs to motivate an ansatz for the corresponding special holonomy geometries. And the interplay between these is rather interesting. And a very interesting question is then whether how much of the mathematics of the K3 story is mirrored here. So to what extent could need to be thought of as a neck region of some compact special holonomy space of generalizing what we saw in the K3. And then it's also interesting to explore what happens if we relate to via dualities to other configurations. But I'm out of time, so let me just conclude. We've looked at the nil manifold and its duals, which give local string solutions by fibering over an interval. And these local solutions being put as part of a full string theory solution by relating to the type 1 prime theory and dualizing, so that we have confidence that in string theory there really are configurations with these properties. And this leads to a particular picture of K3, which has a picture of a nilfold fibered over an interval with Kaluza-Klein monopole insertions and Tian-Yau end paths. And this is a good approximate geometry for K3 that allows explicit duality transformation. And we saw the case of looking at the T-duality, which would be associated with mirror symmetry, and saw that in this case, the K3 would self-mirror. The singularities of the smeared branes are resolved in an interesting geometric way. And in particular, we understand the Tian-Yau geometry as giving the geometric dual of the orientifolds. And in particular, it reveals in a simple geometric way some of the rather obscure non-perturbative physics of the string theory, of its string theory duals. There's the generalization, I very briefly mentioned the generalization to special holonomy manifolds and the relationship with intersecting branes. This is part of continuing work in progress, and it'll be very interesting to see just how much of this story can be generalized and extends to these higher dimensional cases. And an important part of this is part of understanding beginning the understanding in a precise way of the kinds of dualities which are related to T-duality, but are some sort of generalization of that, which don't require exact isometries, but just require isometries at some point in the moduli space. And looking at this problem in the controlled context of consistent string theory backgrounds gives us a way of exploring that and really understanding beginning to understand these relations. And one thing I didn't have time to talk about is exploring some of the what happens if you do more T-dualities, things which will take the nil manifold geometries to the T-fold geometries, which are these non-geometric backgrounds. And one of the reasons why I first started getting interested in this chain of dualities was that I was interested in T-folds, non-geometric string backgrounds, ones where the transition functions are not diffeomorphisms, but are duality transformations. And this would provide a very basic example, a simplest example of a consistent background, string theory background, which involved such geometries. So I'll stop there. Thank you for your attention.
So, any questions? I have like one or two questions.
Yes, so these K3 manifolds you're talking about, can they be also realized by compactive? Because these are particular metrics which are T3 fibered over an interval, right?
Yeah.
Or line.
Yeah.
So I think that can be also realized as as a metric which arises on the Coulomb branch of torus compactified 5D gauge theories. If you compactify 5D gauge theory, a supersymmetric one on a T2, you get the same similar structure. And those and there the petzos play a concrete role because they geometrically engineer these 5D gauge theories. So these 5D gauge theories are SU2 with NF is equal to 0 to 8. And they come exactly from non-compact Calabi-Yaus over anti-canonical bundle of these del Petzos. So might this have something to do with
yes,
that?
Yeah, that's very interesting. There's another interesting part of the story which I didn't talk about. I mean, I mentioned the work of Morrison and Seiberg, and the way they got the clue that there should be this strong coupling behavior was looking at precisely the five-dimensional gauge theory of the kind you're talking about. So that's very much part of the story. And so one application of all of this will be to five-dimensional gauge theories in the way that you...
But I think also in the five-dimensional case, there is a concrete way to resolve the singularities using instantons, because we know what the instantons are, and there are these strings wrapping the torus, and you can compute the contribution very, very concretely. So maybe that will also play into these metrics.
Yeah, that would be interesting.
Thanks.
Any question? Okay, so I have a question. So I also wonder what are the new updates on the understanding of accidental EN symmetry from, say, 11D Sugra on a torus? And do you have more new understanding from this del Pezzo kind of magic, for instance?
Yes, so, I mean, the understanding about what happens in perturbative string, I mean, it's been well understood for many years what happens in perturbative string theory. And the question is, one of the issues is one of whether there's anything more which can happen non-perturbatively. And here what we're seeing is that there's some things which can happen non-perturbatively, which don't happen perturbatively. And that can be thought of as in the type 1 prime picture from the fact that although perturbatively you only got 16 D8 branes to play with, which you can make coincident or put all on one end or look for special configurations. What it's saying is non-perturbatively you've got 18 to play with, and so that gives the possibility of gauge groups which couldn't arise perturbatively in the type 1 prime picture. In the K3 picture, they're all on the same footing, so that they would all correspond to singularities which would arise from the Kaluza-Klein monopoles coming together to make singular geometry. And so that you get singularities resolved in that way. But what's changing is it's telling you that there's more Kaluza-Klein. It's telling you how many it's giving precise information about what Kaluza-Klein monopole charges are allowed in singularity.
Yeah, thank you. Well, I thank Professor Chris Hall again, and you
Thank you.
can go back, come back at 15 past.